Hello, I am Amartya, and this is my presentation on benzene. The structure of benzene. Benzene is an organic chemical compound with a molecular formula C6H6. The structural representation for benzene is a 6-carbon ring, represented by a hexagon, which includes 3 double bonds and a hydrogen atom attached to each carbon. The 3 double bonds are delocalized among the 6 carbons, as it will be shown later in the presentation. The full electron configuration of the carbon central atom benzene molecule. The benzene molecule has 6 central carbon atoms. Carbon has a total of 6 electrons. Therefore, the C electron configuration will be 1s2, 2s2, 2p2. The orbital diagram of the carbon central atom in the benzene molecule. The orbital diagram shows how the electrons are arranged within each sublevel. The maximum number of electrons in an orbital is 2, each with opposite spins. The 1s sublevel has one orbital with 2 electrons, with opposite spins, represented by the arrows pointing in the opposite directions. The 2s sublevel also has one orbital with 2 electrons, also with opposite spins. The 2p sublevel has 3 orbitals, according to Hund's rule. Each orbital must contain 1 electron each with the same spin, before adding a second electron. So in the 2p orbitals, there are 2 electrons, each with the same spin, and the third orbital is empty. The hybridization of the carbon atom in the molecule. Considering the sigma bonds, each carbon atom has to join to 3 other atoms, 1 hydrogen and 2 carbons, and doesn't have enough unpaired electrons to form the required number of bonds, so it needs to promote one of the 2s2 pair to the empty 2pz orbital. So the first thing that happens is promotion of an electron. There is only a small energy gap between the 2s and the 2, and an electron is promoted from the 2s to the empty 2p to give 4 unpaired electrons. The carbon atom is now said to be in an excited state, because each carbon is only joining to 3 other sigma atoms. When the carbon atoms hybridize before forming bonds, they only need to hybridize 3 of the orbitals rather than all 4. They use the 2s electron and 2 of the 2p electrons, but leave the other 2p electron to make a pi bond. The new orbitals formed are called sp2 hybrids because they are made by an s orbital and 2p orbitals reorganizing themselves. The Vesper shape associated with the carbon atoms in the benzene molecule. The benzene ring consists of 6 carbon atoms bonded in a flat or planar hexagon ring. Each carbon is bonded to 1 hydrogen and 2 sigma bonds with carbons, so the total electron domain is 3. Hence, the molecule geometry at each carbon is diagonal-planar, and the angle is 120. Resonance structure of benzene molecule. Using X-ray diffraction, researchers found that all of the carbon-carbon bonds in benzene are the same length of 140 picometers, pm. This length is greater than the double bond, 135 picometers, but shorter than the single bond, 147 picometers. The intermediate distance is explained by electron delocalization of the pi bonds among the 6 bonds, which is called resonance. Aromacity of benzene molecule. The resonance gives benzene great stability. The enhanced stability is the fundamental property of aromatic molecules that differentiates them from non-aromatics. So benzene is often depicted with a circle inside a hexagon arrangement of carbon atoms. Some reactions involved with the benzene molecule. Although benzene contains 3 double bonds, as explained before, the resonance gives it extra stability. Thus, benzene undergoes substitution instead of addition reaction. Examples of substitution reactions of benzene is nitration and halogenation. Electrophilic substitution of benzene. Benzene has clouds of pi electrons above and below its stigma bond framework. Although the pi electrons are in a stable aromatic system, they are still available for reaction with strong electrophiles. There are a wide variety of electrophiles that can be introduced into a benzene ring this way. And so electrophilic aromatic substitution is a very important method for the synthesis of substituted aromatic compounds. General mechanism of electrophilic substitution of benzene. The general mechanism involves 2 steps. Step 1. Attack of the electrophile by aromatic pi bonds. And 2. Deprotonation of the hydrogen. Electrophile means a reagent that like negative and hence itself has a positive charge. The nitration of benzene. The nitration of benzene occurs via electrophilic substitution. The first stage in the reaction is the formation of the electrophile. This is the nitronium ion, or NO2+, which formed when concentrated sulfuric acid reacts with concentrated nitric acid. The second stage starts with the electrophile attacks the benzene ring to form an intermediate carbocation. In step 3, the bisulfite ion HS2O4- takes a proton from intermediate carbocation sigma complex to give nitrobenzene. Molar enthalpy of combustion of benzene using standard enthalpies of formation values. Step 1, we should balance the complete combustion reaction of benzene. Step 2, calculate the standard formation enthalpies of reactants and products using table 12, which is 6 times negative 393.5 plus 3 times negative 285.8 minus 49 equals about negative 3,267.4 kilojoules per mole. Step 3, subtracting the sum of the formation enthalpies of products and reactants, so delta H is negative 3,267.4 kilojoules per mole. Molar enthalpy of combustion of benzene using bond enthalpy values. Again, step 1, we should balance the complete combustion reaction of benzene. Step 2, calculate the bond enthalpies of reactants and products using table 11. So it will be 6 times 507 plus 6 times 414 plus 7.5 times 498 minus bracket 6 times 2 times 804 plus 3 times 2 times 463 end bracket equals about negative 3,065 kilojoules per mole. Then subtracting the sum of the bond enthalpies of the reactants, so delta H is negative 3,165 kilojoules per mole. Yes, benzene is found naturally in the environment, and it's also emitted from industrial sources as it's used to make other industrial chemicals. Benzene is also used as a solvent in the chemical and pharmaceutical industries. Most benzene exposure comes from the air from a number of sources, including forest fires, auto exhaust, and gasoline from fueling stations. Benzene in cigarette smoke is a major source of exposure. Very low levels of benzene have been detected in fruits, vegetables, nuts, and dairy products and eggs. Breathing benzene can cause drowsiness, dizziness, and unconsciousness. Long-term benzene exposure causes effects on the bone marrow and can cause ammonia and leukemia. Thank you.